Thanks very much. So I want to do a little tour, starting from the old Greeks, going to modern developments, the so-called Khovanov homology. So, So what you all know, I guess, is the Platonic solids. Important is there are 5 of them. And the old Greeks already knew that everything is built out of the 5 Platonic solids, so they did control the whole world. So for a mathematician, I can't use this. It's of course interesting to understand the symmetries, so you can group them into pairs, as shown, so that one is the dual poly or the dual solid of the other, and so the symmetry group is the same. So you get 3 symmetry groups. So, but somehow, when you look in the world, you realize that these groups are interesting, but one should study them further. So it was studied using like hypergeometric functions by Schwarz. So he thought about PGL2 as conformal transformations of S2, and then SO3 and the corresponding subgroups which we saw as maximal subgroups of isometries. So, but still, if you look in the world, you see not everything is built up from these solids. So if you look at this guy, you realize it's not a solid, and you can't build it from solids. So how does it look like? It has the 2 poles, north and south poles, and has the slices. And you can have, of course, many slices, say n slices. So you would have a solid which has 2 vertices and n faces. And then you have a dual solid, which you can think of as a calzone pizza. The 2 poles become faces, and then you have a calzone pizza with probably n different vertices at around. So what is the symmetry group of this thing? So Felix Klein figured out that we need more Platonic solids, so at least not 5, but 7, and get a symmetry group of this one, which is the dihedral group of order 2n. So when you see in this list below, there are these 3 groups corresponding to the actual Platonic solids. There's the dihedral group, and then there's one further, which is a subgroup of SO2R, or corresponding double cover SL2C, which is a cyclic group Z mod NZ. So here's my Platonic solid, number 8. So I have on the bottom, I have an n-gon. It has the top piece, and the only symmetry which you have is the rotation. And this is the first cyclic group Z mod NZ. So, and what we want to do now, we want to study these corresponding groups. And Klein came up with so-called Kleinian singularities. So what is behind this? So let me describe this now on the board. So now we do actually mathematics. So we have a subgroup inside, say, SL2C. So it acts on C2. So what we want to study is the orbit space C2 mod this group. But you can either study it from a set theoretic point of view, which is maybe not so interesting. You want to see it from a modern point of view, which means I want to look at functions on this. And because I'm an algebraist, I want to look at algebraics or polynomial functions on this in the 2 coordinates u and v. And I want to ask what are invariants under this. And this should study this quotient here. So let's do an example. The first example in this list, the group Z mod NZ. So you can realize it as a subgroup of SL2C by saying I take all matrices of the form like this. So we have xi and xi inverse on the diagonal, where xi is an nth root of unity. So it's 2 pi I divided by n. So that's a subgroup. And you ask the questions, what are the invariant functions here? So I scale u with xi and I scale v with xi inverse. So for instance, when I take the following function, u to the n, this is an invariant. I can also take v to the n. I can also take minus v to the n. Or I can take u times v, because u gets scaled by xi, and v gets scaled by xi inverse. So they're all invariants. So let me call this guy short y, let me call this guy short Z, and let me call this guy short X. So what are the relations between them? The relations are, of course, x to the n plus y times z is 0. Now, if you look at this list which we had here, in this Kleinian singularities, so it's just the first list except of the shift by 1. So what Klein figured out, that these are all the relations you have to put. And so for any group which we had in the list before, for any finite group G which we had before, we have always these invariant functions determined by a single equation, which is written over there. So now let's look a bit more in detail at the case n equals to 2. So how does this equation look like in n equals to 2? So I have the equation a squared plus bc is equal to 0. So if I look at this, so this is I want to look at it over the real numbers, over the complex numbers, but I can only draw a picture of the real numbers. So over the real numbers, it would look like this. It's a double cone with a 0 point in the middle. Okay, so now if you look at this list of Kleinian singularities, so they are labeled by A and Dn because that's an infinite family of groups, E6, E7, E8. So I'm a Lie theorist or representation theorist. So the same labeling comes up by looking at these graphs which describe, for instance, semi-simple complex Lie algebras. So I want to put this into the context of semi-simple complex Lie algebras. And I can do this, for instance, by saying this equation here is given by all matrices A, B, C minus 8 inside SL2C, so trace 0, such that this equation holds. So, but this equation is nothing else than the determinant, or minus the determinant, is 0. So that means I have a matrix which has trace and determinant equals to 0, and this means nothing else than having a nilpotent matrix. So this is called N. And you can say this is the same thing as all matrices like this, which are nilpotent. So this is called so-called the nilpotent cone, by obvious reasons, because I have a cone given by nilpotent matrices.
I'm completely lost. SL2C, does it mean that the determinant is 1?
No, so this is the Lie algebra SL2C, which is a little s,
Okay, I'm with you.
or German s, which means trace is equal to 0. Okay, so now what we don't like is this singularity. So it's a so-called Kleinian singularity, so we want to resolve it. So let's resolve it like this. So how do I think about it? I think about this. A resolution is over a smooth point. I just have a bijection. And over the singular point, it would be blown up to this little circle, which, because it's a real picture, is in fact a P1. So what is this resolution? So this resolution is T star CP1. So if you think about it, this is a cotangent space of a sphere. So if I have a sphere like this, and I have a point L here, the tangent space is just given here by taking orthogonal vectors. So the cotangent space would take functions on this. So but I can, when I have a function in the cotangent space, say f, I can assign to this a matrix AF by just saying, I want to have the matrix like this, AF. So this is a 2 times 2 matrix. So it defines the map from C2 to C2. It sends the point to 0. And the other, the tangent vector, it should send, so let's say this is y. It should send y to f applied to y times L. So it just sends it to L scaled by this f. So in this way, you can identify the cotangent space with pairs L and A, where this is a line, and this is a nilpotent matrix. A 2 times 2 matrix. Such that this equation holds A, L is 0, and A of C2 is inside L. Okay, so this is a cotangent space, and it looks like this in the real picture. And I have two maps. I have the map projecting to the base point, L. So this would go to CP1. And I have the map projecting to the nilpotent matrices down here, projection 2, which I call mu. So and this is a resolution of Kleinian singularities, and this is called the Springer resolution in the special case. And this plays a very important role in geometric representation theory. So this is somehow the basic building block for many constructions. So it was introduced by Springer around 1970 or 75, like this. So now we have seen that this is the easiest case. So this would be n equals to 2 corresponding to SL2. But because I'm a Lie theorist, we can replace this SL2 by any sort of complex semi-simple Lie algebra. So let's do this and make it more general. So I want to say n is all x in G. G is a semi-simple Lie algebra, like SON or SPN or whatever you want, such that x is nilpotent. So this is a singular variety, and it has a resolution just given by the corresponding space, T star. I write T star G mod B, where G is the corresponding group to the Lie algebra. B is a Borel subgroup, so for GLN, this would be just GLN modulo upper triangular matrices. And you can make this very explicit, generalizing the stuff upstairs. So these are the following elements. These are pairs, F and X. So X is nilpotent. Your map is projection onto the second coordinate, like over there. But you change this line by this F, which is a flag inside, say, C to the n. So it's a sequence of subspaces of dimension 1, inside 2, inside 3, etc. So the special case upstairs would be a one-dimensional subspace inside C2. Okay? So this would be the case when you have, say, type A. So this would be type A. So if you have type BCD, which means it corresponds to the orthogonal or symplectic case, you have also a form on this C to the n. So what you do then is you take, so let me just say I'm in the even case. So you end up in C2n, and then you have a form which pairs these subspaces in the way that Fi orthogonal is F2n minus I. So you have some sort of symmetry pairing the zero space with the 2n, the first one with the second last, etc.
In this definition, there's x and f0 must be related, and this flag must be related in some way, or?
Yes. So I haven't written anything yet about this. So these two things should be now related in the following way. You want that x preserves this flag, so x applied to Fi should be inside Fi minus 1. And if you check upstairs, it's exactly this condition which we wrote here. Okay, so this is the resolution, and I want to say if I take x in here, then dx is, so this is again mu, is mu to the minus 1 of x. This is the Springer form. So what we would like to understand, or what is interesting, is to see how does this Springer fiber look like. And let me just do a little example to give you an idea. So over here it's easy, it's just points, and over 0 it's this phi1. So this is easy, and in particular it's easy and very misleading because the fibers are all smooth. In general, the fibers are not smooth, and this is why they are interesting. So let's do a very small example of type A. So let's take this nilpotent matrix, and let's see how does the fiber look like. So we look at flags, F1 inside F2, inside C3, such that this condition holds. So So let's say, what can we do for the first space? We look for a one-dimensional space which is sent to 0 under X. So what we can do, we can start with, say, alpha E1 plus beta E3. So where alpha and beta is anything. So the next space has to be mapped to this space. So if we take E1 and E3, then this is fine. If we take the second basis vector, then it can only map to here if E3 is not occurring, because the second basis vector is mapped to the first. So I can take here E1, and I can take here, say, alpha E1, alpha E2, plus E3. And I claim this is all what I can do, so that it's fixed. So what is this? How does it look like? So what you see here is a two-dimensional space, where you pick out a one-dimensional space. And what you see here, this is a fixed one-dimensional space, so we can ignore it. We can factor it out. You see in the quotient a two-dimensional space, and you again choose a one-dimensional space. So these are all CP1s. So these are two CP1s, this one and this one, at least if you take the closure. And how are they related? If you look carefully, in here I have the point E1 by setting beta to 0. Here I have E1, E3. But here I can set alpha to 0, and I have, sorry, I should have written E1 like this. So I have here, if I set alpha equals to 0, I have E1, E3. So what I claim is that you have two CP1s. So one is this guy, the other one is this guy. And they intersect here in this point where I have E1 inside E1, E3. Okay? So in general, if I would take here a block of size n and here a block of size 1, what I would get is a chain of spheres glued together so that they always, when they are neighbored, they intersect. And so let's go back to this picture. So this picture is standing for classification of semi-simple complex Lie algebras. AN is SLN. But if you look just as the graph and replace every point by a P1 or a sphere, somehow the arrangement of the spheres looks exactly like the graph which you draw here. And this is true in general. This is also true in the other types. So if you do this sort of correct choice of nilpotent, you get this resolution which looks like spheres glued together. But this is only for very, very special cases, namely for these Kleinian singularities. So this picture is much more general. I can choose X much more arbitrary, so I get more than these things. So now, these things, as a complex algebraic variety, these are so-called irreducible components. And so we can ask the question, can we in general understand irreducible components for arbitrary x? So and here's a theorem by Spaltenstein and Vargas. So this was roughly 1976 for type A, and Van Leeuwen much later in 2012 for other type A. So what does it say? So if I have an X nilpotent of Jordan type, lambda. So what do I mean by this? So lambda is a sequence of numbers, lambda 1, bigger or equal lambda 2, bigger or equal lambda 3, etc. So that's a sequence of natural numbers, and it just tells you the sizes of the Jordan blocks. So in this case, it would be 2, 1. Okay, so I fix this. And then the statement is the following. So it gives a classification of irreducible components in terms of combinatorics. So irreducible components of the Springer fiber, X, correspond one-to-one to some combinatorics, and this is the so-called standard tableaus. Standard tableaus of shape lambda. So what is a standard tableau of shape lambda? A standard tableau, I just give you an example, or maybe two examples, and then you can see what it is.
Isn't it usually called Young tableau?
So a standard tableau is a Young tableau where I put in extra data. So a Young tableau is you put just the lambdas as an arrangement, so it's a number of boxes in one row. So this would be, say, 2, 2. And a tableau is putting inside here the numbers 1, 2, 4, such that it's increasing in this direction and increasing in this direction. So in this case, I have two possibilities. Oops. I can do. So the 1 has to go here, the 4 has to go here, but I can swap 2 and 3. Okay. So and for instance, in this case upstairs, maybe I put this here. In this case upstairs, I have 2 possibilities, namely these 2. Okay, so now the bijection is extremely easy, somehow. So we take such a tableau, T, and we assign to it a space of flags, such that F has Jordan type, or Jordan sequence, T. So what do I mean by this? So I have this T, and this the point that I ordered it in this way, increasing here and increasing to the bottom, means when I remove the 4, I still have such a tableau. If I remove 3 and 4 again, etc., so I get a sequence of such tableaus. And I can ask the question, when I restrict to the subspaces, like the first 3 ones, what Jordan type do I have, etc., and see what happens. So let's do this in this example. So here, in C3, I have my Jordan type of X to be 2, 1. Then I restrict to here. So here I have the basis vector E1, E3. If I look at my Jordan type, I have this box 0 here and the box 0 here. So the restriction is then the Jordan type is just 2 blocks, like this. And I should have swapped it. So which means when I remove the 3, I get exactly this type. And this is the Jordan type restricted to this subspace. Then I restrict to this subspace. It's of course one-dimensional. I have only this guy left. So if I do this example, I restrict to here. I have an E2 sitting here, which means I have a Jordan block of size 2. So that means I get Jordan block of size 2, and I get this sequence. So that means here I have this sequence, which corresponds to this first standard tableau. And there I have the sequence which corresponds to this standard tableau. And so in general, I take the standard tableau, I take the corresponding flags of Jordan sequence type T, and then I close it up. And this is my irreducible component. And so it's extremely easy to classify them. The difficult thing is, so without the closure, it's very nice. The closure is extremely hard to understand in general. Okay? So now I want to, and I should say, this is type A. If I do other types, so say type B, C, D, then this notion of standard tableau is a bit more interesting. So in this situation, it's the standard tableau which comes up like in the representation theory of symmetric groups and in combinatorics, etc. In type BCD, you get something which is a bit more interesting. Namely, we saw that we have these flags which have additionally this property with respect to form. So it's somehow symmetric. So if I do this game by removing subspaces or restricting to subspace, you should remove one at the end and one at the beginning, because otherwise it doesn't stay symmetric. So I want to have isotropic flags, and this means I should remove at least an even dimension. So to do this, I work not with standard tableaus, but instead with what is called domino tableaus, or standard tableaus of type BCD. So you would get something like dominoes. So for instance, something like that, which you always have pieces of 2. And again, you fill in numbers. And again, it has to be decreasing in this direction, and increasing in this direction, and increasing in this direction. And you play the same game, and you have the same corresponding classification. So this is this result due to Leuven. This was only proved in 2012. Okay. So what I'm interested now is to study this Springer resolution somehow as a variety. So I understand the components, but I don't really understand how it looks like, how they are glued together, except of these small cases where we saw it's a sequence of P1s.
Just a curiosity. When you work on the right side, on the young tableau,
yes,
there's also an actual measure on the
yes,
partial measure. Does that correspond to something interesting on the
yes,
singularity side?
Yes, it does, but it's more complicated. We can discuss it later. Yes. So what I want to understand now is this irreducible components as topological spaces. Or the Springer fiber itself as a topological space, because it's easier than as an algebraic variety. So what I do is I give you a few examples to give you an idea how this might look like. So I start with a standard tableau, and this is my favorite one. Let's say I do this example. I assign to this a diagram. So D stands for diagram, and C stands for component, and top stands for topological space. So I do just something very easy. So I have here 4 numbers, 1, 2, 3, 4. And here I have 4 numbers, 1, 2, 3, 4. But I encode how they are put into these boxes. So there's 1 and 2, they're at the top. So I indicate which ones are in the top. And here 1 and 3 are in the top. Like this. Then the others are in the bottom. Let me indicate them like this. So now there's a unique way to connect these downs with ups so that I don't intersect. So I get this. So we can do another example here. So here I would have 3 points. 1 and 2 are on the top, 3 is on the bottom, and I can connect them. So, and this has to stay over because it's not none. Okay. So now I assign to it the topological space, and it should be, because I think of it as being glued together from spheres. Everything is supposed to be inside S2s for copies. S2 4 copies, and here S2 3 copies. And the rule is extremely easy. The rule just says, take the subspace in here, given by the incidence points, or incidence set, determined by this diagram. So whenever I'm connecting, I have the same point. So I have x and y, but then here it's connected. I have x and y. Oh no, I didn't do it correctly. Y and x. So the first and the last is connected, and second and third. And here I have this guy. X, x, y, y. Okay? Here I would have the following. I would have points. The first one is ray. This is just a fixed point P, say the north pole of S2. And then I have xx. Here I would have xx and P. So what you get is a subset of spheres, and you see exactly how many spheres I have, namely as many as I have arcs, but they are embedded in different ways. So for instance here, they intersect in the point PPP. So I have exactly this picture which we wanted to have from before. in this case, I have a sphere with this axis. I have a sphere here, and they intersect in the point P, P, P. Here, I have two spheres. Here I have two spheres, and they intersect, obviously, in x, 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 which is a sphere again. Okay? So, and I claim that this very easy topological picture describes the Springer fibers, at least in the case when I have only two Jordan blocks. And so, for people who know like Morse functions, etc., you can think of them, of this construction as being the following. So these indications with ups and downs, you can see as a fixed point for a torus action. So this is a coordinate flag. So say whenever I go down, I take coordinates from the first block, 1 and 2. And whenever I go up, I take coordinates from the second. You can write down a fixed point. And what I write down here, somehow explicitly and easily, is an attracting cell for a torus fixed point. This is what is behind this. And so here's the theorem. So this was started by Fang in 2003. And then we did this, I did this with Ben Webster for type A. And then with Eric for other types. And it says the following. Let X be nilpotent with two Jordan blocks, or at most two Jordan blocks. Then first of all, this irreducible component in an algebraic sense is homeomorphic to the irreducible component in the topological sense. So this is a model as a complex variety or complex manifold. So when it's they are iterated P1 bundles. So this is for the algebraic.
I'm sorry, I've lost who C.
So this is CT is the irreducible component as an algebraic variety. And this is as a topological space in this naive sense, and it's homeomorphic. And I claim as an algebraic variety, it's an iterated P1 bundle, and as a topological space, it's an iterated C2 bundle. But here, as a topological space, they are just trivial bundles, whereas as a algebraic variety, there would be a difference between that and that. Here, this would be just CP1 times CP1, whereas this would be a non-trivial iterated bundle. And you can see this from the picture because this is not nested and this is nested. Okay, second statement is when I take the intersection, this is again an iterated P1 bundle. And in particular smooth. So this is special for this small case of two Jordan blocks with the number of P1s equal to the following thing. So let's play a game. I want to compute the intersection in this example. So I compute this as in the following way. I look at the first component, and I look at the second component, and I put them on top of each other. And I just ask by looking at the intersection, which points can I put like this? So if I put an x here, it tells me if I go along this line, I have to put an x here. If I go along this line, I have to put an x here. If I go along this line, I have to put an x here. So there's one choice of x's. And this means its intersection is a S2, or P1 again. So the statement is the number of P1s which occur is the number of circles in the picture when I take the diagram for T, and I take the diagram for T primed upside down, like this, and I just count. So it's extremely easy to see how large this is. So for instance, when you take the intersection here, I take this on top, and this is just a line. So you would have here the point P, this has to be the same, this has to be the same. So whenever I have a line, I just get a point as an intersection. So this doesn't give me any big contribution. So in particular, if I want to calculate the cohomology of such an intersection, then this is nothing else. If I do it over complex numbers, it's nothing else than the cohomology of P1, which is Cx mod x squared, tensored as often as R, where R is this number. Okay? So, and I want to see this construction, or at least for me, it was a motivation as an easy model of a Fukaya category. So if we don't look at these cases where I have not the same number of boxes, but let's say I have the same number of boxes on top and on bottom, I have here a space which has S2 to some even number. I mean, how many copies I take is even. So I can put a symplectic structure on this if you want. And what I have here is just Lagrangians. So I have subspaces of half dimension. So what I want to do is I want to say I have a category. So it's an easy model of a Fukaya category. So I have a category where objects are irreducible components for this fixed nilpotent, and morphisms are the spaces. So these are morphisms from CT to CT prime. And so morphisms from CT to CT prime is just the cohomology from CT intersected with CT prime. And you can put a composition on this by not doing it in the naive way, doing this as a commutative ring, but putting a convolution product structure on this. So this is convolution product. So in particular, it matters whether you have the CT here and the prime here or vice versa. So the space is the same, but when you of course compose, it makes a difference. So and indeed, so this easy model of a Fukaya category was realized as a Fukaya category by Seidel and Smith in 2006. So they constructed some Fukaya category associated to slices to nilpotent orbits, and they worked with it. And then just recently, Abu Zaid and Smith realized that this is indeed the same construction and as this, showing that on the Fukaya category side I have no higher multiplications for this, no infinity structure really, so it's formal, and this was done in 2019. So this very easy model has a real incarnation as a Fukaya category. So and if you just as a remark, if you want to go away from type A, then you have this sort of domino tableaus like this. And so let's say I have a tableau like that. And I would play the same I would play the same game as I did over there with the ordinary tableaus if I just have no vertical dominoes, just horizontal. I just view them as a normal tableau. So I would have 2, 3, 4, 5. This looks exactly like this one, except that everything is shifted. So here I would just assign this guy. And when they are vertically, I would connect them and put a dot. So and for the topological space, this is just the same thing, except that this dot gives a different embedding. So if I have, so in the middle I have y, z, z, and if I have connection with the dot, I put a minus x instead of x, and so I have say w minus w. So, and this is again inside S2 to some whatever. And the statement is exactly the same for these guys. And for people who know representation theory, this dots, this refers to some folding. So it's connected with passing from a Temperley algebra of type A, which is a quotient of a Hecke algebra of type A, to a quotient of a Temperley algebra of type BCD, which you can draw like diagrammatically. So good. So this is my space. And of course, the new developments are generalizations of these Springer fibers in all different directions. But I said at the beginning, in my title of the talk, that I want to say something about Khovanov homology. So Khovanov homology is something totally different. Somehow on the first sight, it's an invariant of knots. So now let's do topology. And let's say I want to have a knot or a link, and I want to construct an invariant. So and there are very famous invariants, like the Jones polynomial or the Alexander polynomial. Important is they are polynomials defined over integers. So the value is a polynomial or a Laurent polynomial defined over integers. And what I'm interested in is to categorify this, which very easily means the following. If you give me a polynomial with coefficients, say, in natural numbers, I want to realize this as a graded dimension or Poincare polynomial of something. And this is what Khovanov did. And you can do this. One version of it is doing it using these Springer fibers. And I just want to indicate this very quickly. So Khovanov homology was defined by Khovanov in 2000. Oops. And it does the following. So let's say we have a link like this. So that's a link diagram. So now what topologies do is they say, take these crossings and remove them, resolve them. So we do this by saying, okay, the first crossing I resolve in this way. And in general, I can resolve it in two ways, namely either in this way or in this way. And for people who know what the Jones polynomial is, topologists would usually write down a scale relation which says something like this crossing is Q minus this crossing. So we do this now in this special example. So I take this crossing and I resolve it both in the same way. Now I can resolve the first one in a different way, or I can resolve the second one in a different way, or I can resolve both of them in a different way. Okay? So I just replaced these crossings by either two vertical strands or two horizontal strands in all possible combinations. And now I close it. So maybe I close it with a color. I close it as it was closed before. Okay, so these are pictures now, which give me a resolution of this diagram here. So now I want to think as this picture as naive as in the thing upstairs. So whenever I had this sort of cup diagrams, I could assign to it a topological space. I do the same thing. I assign to it a topological space by just saying, assign to this a subspace in copies of C2, where you just say for each circle I put X, and when they are connected I put X. So that means here, this is just two spheres. This would be one sphere, this would be one sphere, and it would be two spheres. So and let's take now of this topological space the homology. So what do I get? The first thing, these are two spheres. I get the cohomology, which is Cx mod x squared. So maybe I abbreviate this. R is Cx mod x squared. So I get here R tensor R. Here I get one copy. Here I get one copy. And here I get two copies. Like this. And now instead of having just a number as an invariant, these are vector spaces. So I might have a map between them. So I sum them up column-wise, and I put maps in between. So I sum them up here. I put maps in between. So which map can I imagine to put here? This is R tensor R, so I can multiply them to get R. I can multiply here to get R. So now, this here is not only an algebra, it's a Frobenius algebra. So it has a non-degenerate associative pairing. So I have also a co-multiplication going from R to R tensor R, sending 1 to X tensor 1 plus 1 tensor X, and sending X to X tensor X. So I can put this here. Okay, and if I put a minus sign there, and you sum this up, what you get is a complex. So that means this map composed with that map is 0. So, and this is what is called the Khovanov complex. And this, because this is graded, it's a graded vector space. This is a complex of graded vector spaces. And I'm a bit sloppy with putting grading shifts. One has to shift this a little bit, but let's ignore this. I get a complex of graded vector spaces just built from viewing this diagram of a knot, resolution, and then assigned to these pictures here in the naive way as before, an algebraic variety or a manifold. So, and the theorem of Khovanov is this complex up to homotopy is an invariant of oriented knots or links. So how does the orientation come into the picture? So if I'm honest, I have to orient this, so this becomes an orientation. And then I have to resolve this in this way. If I would swap the crossing to the other crossing, then my resolution would be opposite. I would start with this resolution at the top, and then have the two vertical lines to the left, and I would have the two vertical lines to the right. So just the question in which order I would do it would tell me how this is oriented. So this is Khovanov's theorem, and in fact it categorifies the classical Jones polynomial by saying this is a complex of graded vector spaces. If you take the corresponding Euler characteristic, you get a polynomial or raw polynomial in Q, and this is the Jones polynomial. Okay? And just as a remark, so this is ongoing work which we do at the moment, which we are writing up, is in types BCD. We get not invariant of links, but we get invariant of links or knots. So these links would live in R3, which I think of R2 times R. But here, these are in R2 times R, where R2 has a Z2 cone point. So we don't have a puncture, but we have a cone point, orbifold, Z2 orbifold, and we look at knots in this. This is how these other types come in. Okay, so what is behind this picture really is this. Maybe I should draw it in this picture here. Behind this picture is a two-dimensional topological quantum field theory given by this Frobenius algebra. So what we have here, we have these two these two circles sitting here, you assign to them these corresponding vector spaces. So that means I have a functor from compact one-manifolds to vector spaces, which is a monoidal functor, so union becomes tensor product. So here I would assign this guy, here I would assign this guy, and here I would assign this guy. And then to maps, we would assign a cobordism. So that means here I would do this, and here I would do that, and here I would do this guy. So, and the fact that there is this TKFT, two-dimensional topological quantum field theory behind, is responsible for the fact that it's working. And there's, of course, generalizations by now by replacing this ring by other rings and getting not only the Jones polynomial, but higher SLK invariant, and all this works. But somehow it's not as easy to write down as this one. So why would we be interested in categorification? So one motivation, at least for me, is somehow opposite to most people who do knot theory. So my motivation would be this sort of picture coming from knot theory tells us a lot about the Springer fibers, which wasn't known before. On the other hand, you might be interested to construct higher dimensional topological quantum field theories, which might be possible when you categorify it. But also, if you categorify, so that means these things become vector spaces, not just polynomials, you have an extra layer of freedom to do something. So, for instance, if I have this somehow triple knot here, I can find maps from this triple knot to this triple knot. So in general, you can imagine you have one knot here, and you have one knot here. You define an invariant in this way. Then you can think of, can I find a map corresponding to cobordism going from this knot to this knot? And let me finish by this. So Carter, Rieger, and Saito gave a list of so-called movie moves. So I only drew here the movie moves 11 to 14. There's a whole list, which says when I have a tangle or a knot on this side and a tangle and a knot on this side, when are they equivalent? Of course, you can write down some sort of Markov moves in topology, but you really want to assign to these moves some topological cobordism going from there to there. And they write this in terms of moves. So each of these guys is a topological space where you see these pictures as being horizontal cuts of this space, and you just write in each step when something interesting happens. So for instance, maybe I'll show you the next piece, that it's easier to see. Yeah. So for instance, this here is a cobordism where on one side you start with these two lines, and at the top you end up with these two. So this is a saddle, and this is the corresponding opposite saddle. And these ones I let you draw because I cannot do this, or imagine I cannot do this. And so he has all these sort of moves which you have to satisfy. For instance, here are surfaces which are responsible for Reidemeister moves, which say that when you apply them, the two corresponding knots is the same. Then there are some easy moves like a height move, or this height move. And so the claim is that this Khovanov homology can be upgraded to an invariant not only of knots, but an invariant of knots and cobordisms between them, or even an invariant of tangles and cobordisms between them by checking these movie moves. So this was done already by Khovanov and then by Rasmussen, and they figured out that everything works up to a scalar. But now, just recently, we were also involved in this work, we figured out if you change it slightly, one can actually make it a real invariant. And so this is sort of stuff one would like to generalize at the moment into higher dimensions. And what we believe is that these sort of geometric representation theoretic categories like these Springer fibers give a rich structure which give examples for these things. And I think I stop here. Thanks.